Hello, this is Gary Sherman of Whaddadunce.com. Today, in the videos on valuation basics, we will value a term bond. A term bond is a bond that makes fixed coupon payments over a given term, and at the end of the term, the face value or principal value is returned to the bondholder. So in this section, we will determine, what price should that term bond sell at. The way that these videos are structured is we start with a hypothetical problem, develop the mathematics to solve that problem, and then actually get in there and solve the problem. So here is our hypothetical problem for the term bond. We are tasked with determining the market price of a term bond given the following parameters. So the bond face value, you can look at that as the principal value. So in this case, we have a bond that's going to have a principal value or face value of $100,000. So at the end of the term, $100,000 will be remitted to the bondholder. And what we want to do is we want to determine the market price of that term bond. So we're going to look at a 5-year bond, and we're going to assume that the number of annual coupon payments is 1. Now, the coupon payments, you can look at those as interest payments. And the coupon payment, the number of coupon payments can be one every year, annual, can be biannual, could be monthly, could be pretty much anything. But in order to keep this simple, we will assume that we have a bond that pays one coupon payment at the end of every year. We will assume that the coupon bond rate is 4.75%. Now, this 4.75%, it could be anything. I mean, the issuer of the bond determines the coupon rate. Has nothing to do with market rates. It has, basically the bond holder or the bond issuer is free to set that coupon rate at anything that he or she wants. We will assume that the annual rate of return, the real rate of return, is 2.25%. The real rate is what I want to earn after inflation. So the way that we can kind of gauge what that rate should be is we can take, let's say, the 10-year Treasury and subtract out the inflation rate. The inflation rate can be obtained from a number of sources, but in this case, the 10-year Treasury is about 4.5%, and if we subtract out the inflation rate of about between 2 or 3, we get a real rate of return around 2.25%. So that real rate of return is going to fluctuate every month, but for now, for this video, we'll use 2.25% as the real rate of return, which is the rate of return that the bondholder wants to earn after inflation. We'll assume the inflation rate is 2.75%. The Fed's inflation goal is around 2%, but the most recent inflation print as of June 2026 has been a little north of 4%. But for now, we'll use an inflation rate of about 2.75%, which is somewhere between those two goalposts. And we'll assume that the annual risk premium is 1.7%. Now, the risk premium, we're going to value a term bond that is defaultable. Treasuries are not defaultable. The Treasury can always print money to pay you back the principal, dollar for dollar. But in the case of a corporate bond, the bond is defaultable, which means that the corporation can go belly up, stop making coupon payments, and never make their principal payment, at which time the bondholders basically, what happens is the corporation declares bankruptcy, the assets are sold, and then there's a schedule as far as how that cash is going to be distributed. So the bondholders may receive 40 cents on the dollar. So that 60 cents on the dollar is gone forever. And we have to put in a rate that basically the probability of default times the loss given default. That'll be the average amount that bondholders will lose, on average, given that the rating of that bond. But for now, we'll assume that's 1.7%. In this slide, we want to take a look at some calculations. The first calculation we want to make is equation E1. That's the market value of the bond today. We're going to basically say that the value of the bond is a capital V, and subscript 0. The subscript 0 pretty much means that it is related to time. So V subscript 0 would be value today. V subscript 1 would be value at the end of year 1. V subscript 2 would be value at the end of year 2, and so on. So the value of the bond today is going to be the value of the coupon payments. We'll receive 5 of them, plus the value of the bond face value, which we'll receive at the end of the term. The second calculation we want to make is the coupon payment itself. We're going to receive 5 coupon payments, one at the end of every year for 5 years. So that's equation E2, and we're going to say the capital C is the coupon payment. And the calculation there is the coupon payment equals the bond principal times the coupon rate. So in our case, we have a $100,000 bond, and we have a coupon rate of 4.75%. And if we multiply those two together, we have an annual coupon payment of $4,750. So for every year for the first 5 years of this term bond, we're going to receive $4,750 as a coupon rate, or as a coupon payment, which is basically the interest payment. Now the third calculation is equation E3, and this is the market interest rate. We're going to say that's small k. The market determines what it wants to earn in this bond. But pretty much looks at the credit rating, which can be AAA, triple B, single B, etc. And the market expects to earn a rate on the triple B bond that is higher than the AAA bond. That's because the triple B bond is riskier than the AAA. The same thing with a single B bond. The market interest rate that the market expects to earn on a single B bond is higher than the triple B bond because the single B bond is riskier. So the way that we determine K is we say that the market rate is, or this is what the bondholders expect to return annually on this bond, is going to be the real rate of inflation, or the real rate of return, excuse me, plus the inflation rate plus the risk premium. And in our case, if we go back to the model parameters, the real rate of return is 2.25%, the inflation rate is 2.75%, and the risk premium is 1.7%. So if you add all those together, the market expects to earn 6.7% on this bond. Now the insight here is the coupon rate is 4.75%, but the market rate is 6.7%. So this bond will sell at a discount. If it's sold at face value, then the bond would earn the coupon rate of 4.75%. But according to the market, that's not enough. They want to earn a rate that's higher than the coupon rate. So therefore, the bond will sell at a discount. In this slide, we want to take a look at some bond value equations. So if you look at E4, this is the equation for the price of our bond at time 0. You can see that what we're doing is also note that if I discount something at 1 plus K, then I earn K. You can prove that mathematically. That's pretty much a no-brainer. So what we're doing is we're taking all the coupon payments. In this case, we're saying that the bond price in equation E4 is equal to the first coupon payment divided by 1 plus K to the 1 power, because we have to wait a year to get that payment. And then the second part of that equation is C over 1 plus K to the 2 power. That's the coupon we pay or we receive at the end of year 2 that we discount at 1 plus K to the 2 power. And we do that throughout. And note that at the very end, we receive both the coupon payment and the face value. So what we do is in order to determine what that cash flow is worth, we discount at 1 plus K to the 5. So then we want to look at E5, which is basically equation E4 rewritten. What we've done is that rather than have all those coupon payments being discounted separately, we want to state the equation in something that's more manageable. Imagine that you have a 30-year bond that pays monthly coupon payments. Well, that's 360 payments that you have to discount individually. So what we want to do is represent that in a form that's more usable. And what we've done is we've taken equation E4 and expressed it as E5 by using the summation, the sigma symbol. And basically that's a sum. So if you look at the subscript of the summation is t equals 1. T in this case is years, number of years. And then the superscript to that sigma symbol is 5. So what we're doing is we're going from year 1 through 5 and discounting all those coupon payments, and then we're adding the value of the face value, or the face value of the bond. So we're basically saying is that the face value today is worth the face value to be paid in year 5 divided by 1 plus k to the 5 power. And then we want to look at E6. We want to define a discount factor, and we're going to say that theta is our discount factor, and that's equal to 1 over 1 plus k. The discount factor tells us how much I am willing to pay for $1 received in the future. So if I receive a dollar, if today is time 0 and I receive a dollar, that dollar is going to be worth $1. But if I have to wait a year, it's going to be worth something less because I want to make a return on my investment. So what we do is E6 is we define theta, and then we note that all of the 1 plus k's in equation 5 above go away. So all we're doing is we're expressing equation E5 into E6, where rather than having the 1 plus k's, we have a theta, which is a discount factor. And then, but really that doesn't really do anything for us because if we just use equation E6, what we have to do is we have to actually walk ourselves through that summation, that sigma symbol. So what we would do is we would take theta to the 1 and then add theta to the 2, then add theta to the 3, then add theta to the 4, and then add theta to the 5. So really that doesn't save us any time, but it does state the problem in a format that we can work with. And at the end, end of that equation, we want to know what the discounted value of the face value is. Remember, we're going to receive the face value at the end of year 5. So the value of that face today at time 0 is going to be the face value times our discount factor to the 5 power. And then we go to E7. In E6, because we have to walk our way through that summation, what we want to do is note that summation in E5 or E6 is actually a geometric series. And what that says is that if I have a geometric series where I'm adding up the theta to the t power, so in other words, I go to that summation symbol and note that I start at 1, and then the superscripts say I end at capital T, which is a bond term. So rather than sitting there with the calculator and just taking theta to the first power, adding theta to the second power, add theta to the third power, et cetera, there's a closed form solution to that summation, which is a geometric series. And that geometric series, it can be stated as the numerator is theta minus theta to the capital T plus 1. So in our case, the discount factor is x. And we would take x minus x to the t plus 1. The t in our case is 5 years. So that would be theta minus theta to the 6 as a numerator. And then the denominator would be 1 minus theta. Now this works if theta is greater than 0 and less than 1, which will always be the case in the kind of math that we're using for the valuation of financial assets. And then the capital T is a bond term. So if I take E7, that geometric series, and plug it into E6, so in other words, I'm taking the sigma equation in E6, and I'm substituting E7 in there, that the solution to that geometric series, then I come up with equation E8, and this is the value of our bond expressed in the simplest terms that we can use. So the value of the bond at time 0 is my coupon payment times the result of the geometric series, and then I add in the discounted value of the face value, which I receive in year 5. This slide takes a look at the discount factor over time. And remember that the discount factor is what I would pay cents on the dollar that I would pay for $1 to be received at some period sometime in the future. What would I pay for that today? And if you look at E7 in our problem parameters, the discount factor for our problem is we take theta divided by 1 over 1 plus k. And remember, k is the market rate of interest, which is 6.7%. So the discount factor would be 1 over 1 plus 6.7%, which is 0.93721. So what does this mean? This means that if we look at the table to the left, we're going to go from year 0 to year 5, and that's the term of our bond. And the discount factor is in that second column. And what that means is that if I'm currently sitting at time 0 and I receive $1 immediately, what would I pay for that dollar? Well, obviously I would pay dollar for that. So our discount factor would be 1, which is stated at 0 power. If I had to wait a year to receive that dollar, what would I pay for that dollar today? I would pay theta to the 1 power, which is 0.93721, which is what I would pay is approximately 94 cents for that dollar today, knowing that I'm going to receive that dollar at the end of year 1. The same thing with year 2, same thing with year 3, 4, and that final payment in our bond calculation. What would I receive for that, or what would I pay cents on the dollar for that final payment? I would pay theta to the 5th power, which is 0.72307. So what that says is that whenever I get my coupon payment and the face value at the end of the bond term, I'm willing to pay approximately 72 cents on the dollar today for that payment to received at the end of year 5. And if we look at the graph, we can look at this graphically, the discount factor over time. Note that we start with a discount factor of 1, and then at the end of year 1, it's something less. At the end of year 2, it's even something less. So if we took that graph and extended it out, rather than going from year 0 to year 5, we went from 0 to year 20 or 0 to year 50, we would know that that discount factor decreases and decreases and decreases till it approximates 0 at some point in the future. In this slide, we're going to value the bond the hard way. So we're going to use a spreadsheet. And what we want to do is, at the end of the day, we want to value bonds via an equation, like just a closed form solution, an equation, rather than using a spreadsheet. But it's good to do it the hard way first, and then boil things down to an equation, and then compare the results that we get. So what we're going to do is we're going to do valuation option 1, which is value the bond via a spreadsheet. And so what we're going to do is we're going to value each bond principal and interest payment in a spreadsheet, and then add up all those values. And imagine that we have a 30-year bond with 12 annual payments. The spreadsheet wouldn't contain 5 rows. It would contain 360 rows. So the equations, believe me, they come in handy. So what we have is, if we look at the left-hand side, we have a 5-year term bond. The coupon rate we determined to be 4.75%. And remember that the issuer of the bond determines the coupon rate. Now, the market rate is determined by the market. This is what the market wants to earn on the bond. It doesn't really care what the coupon rate is. It wants to earn 6.7%. And then theta, we determined that this was the discount factor. This is the cents on the dollar that we would pay at any given point in time. So if I'm going to receive $1 at the end of year 1, if we go back to the previous slide, then I'm willing to pay 93.721 cents today for that dollar, and so on and so forth. The principal payment, which is the face value payment, we're going to receive at the end of year 5, so that's $100,000. And then the coupon payment we calculated to be $4,750. So if we go to the second segment, or the second segment or section of that spreadsheet, we're going to basically have a spreadsheet with 6 columns. Column A would be the year. We're going to go from year 1 through 5. Column B would be the coupon payment. Remember that we're going to receive a coupon payment at the end of every year. So every year has a 4,750 attached to it. And then column C is a principal payment. We're not going to receive any principal in year 1, 2, 3, and 4, but we're going to receive that principal payment at the end of year 5. And then we're going to add those up. Column D is the total cash flow on our term bond, and this is what we want to value. What we want to say is that we're going to receive $123,750 over a term of 5 years. What would I pay for that cash today? And that's where the discount factor comes in. We noted that in year 1, I'm willing to pay 93.721 cents on the dollar for that cash flow to be received at the end of year 1. So therefore, I would take my cash flow, which is 47.50, multiply it by my discount factor. So for that $4,750 coupon payment at the end of year 1, I'm willing to pay $4,452 for today. We do that the same thing for year 2, same thing for year 3, same thing for year 4. And then note in year 5, I'm receiving the coupon payment and my principal payment or my face value. So that payment is going to be $104,750. The question is what would I pay for that today? And what we do is we take the discount factor to the 5 power. And just like in the previous slide, we determined that for a dollar received in year 5, I'm willing to pay 72 cents approximately per dollar for that dollar. So the value of that $104,750 to be received at the end of year 5, I would pay $75,741 for that today. So if we go back to our bond value equation, we add up all the values or the present values, which is basically the discounted value of all those bond payments, coupon and the face, and I add those up. So what this spreadsheet says is that given that the coupon rate is 475 and the market rate is 670, I would be willing to pay 91,940. And remember that we noted in a previous slide, our insight is that given that the coupon rate of 4.75% was less than the market rate, then this bond is going to sell at a discount, which is exactly what it was happening here. The face value of the bond is 100,000 and the market value is 91. So it sells at a discount. It should also be noted if I went back in the spreadsheet and changed the coupon rate to 6.7%, which is equal to the market rate, then the market value of that bond would be 100,000. So in other words, it would sell for par. In the previous slide, we valued the bond the hard way, which was using a spreadsheet and valuing each cash flow separately and then adding them all up. For valuation option 2 is we value the bond via a closed form solution, which is basically saying we're going to be using an equation to value this bond. So if we go back to one of the previous slides, equation 8 was the bond value expressed as a closed form solution or an equation. So E8 is that equation for bond value. So all we want to do here is that we want to start plugging in our model parameter values into E8 to solve this thing. So what we're going to do is determine that the market value of the bond, of the term bond, is going to be the value of the coupon payments plus the value of the principal payments. So therefore, we take E8 and we look at it in 2 pieces. The first piece is that capital C times the answer to our geometric series. And then the second part is the face value times the discount factor. So E10A is the value of the coupon payments. So we plug our model parameter values into that first part of equation E8. So we have a coupon payment of 47.50, and then we have that geometric series where the value is our discount factor minus discount factor to the 6th over 1 minus the discount factor. And if we multiply those out, we can state that the value of the coupon payments alone are worth $19,633.39. Then we want to value the face value via the second part of equation E8, which is that F times the discount factor to the 5th power. And that's exactly what we do in equation E10B. The value of the principal payments is going to be the 100,000 times our discount factor to the 5 power. And so we determined that was the value of the principal payments here is 72,306.59. So for bond price, that's going to be equation E10C. That's going to be the sum of the value of the coupon payments plus the value of the principal payments, which is 19,633 in equation E10 or E10A plus the value of the principal payments in of 72,306.59 in equation E10B. So E10C is the market price of the bond, and the answer to our hypothetical problem. Add those things up, the bond is worth 91,939.98. And if we go back to our spreadsheet, that's exactly the number we get. So we've used the spreadsheet to validate as kind of a check on whether our equation for bond value actually gives us a good result, which it does. So we've went through all the pain and suffering of calculating the market price today of a 5-year term bond. So what have we learned? What can we glean from the previous slides? Number one is that the coupon rate is set by the bond issuer. The bond issuer can pretty much what they'll do is they'll look at their cash flow situation and say, well, they can afford to make a coupon payment of let's say 2%. Or they might say, well, we want to make a coupon payment of 10%. That's up to the issuer of the bond. Now, the second item there is market rate equals the real rate plus the inflation rate plus the risk premium, and this is set by the market. The coupon rate is set by the issuer. The market rate is set by the market, and the difference between those two is going to, or the comparing those two is going to dictate what whether that bond will sell at a discount, whether it'll sell it at a premium, or if it'll sell at par. Item 3 there is bond price equals the sum of discounted payments, principal and interest. Item 4 is that if the coupon rate is less than the market rate, then the bond will sell at a discount. And that is exactly what happened in our hypothetical problem. Number 5 is if a coupon rate is greater than the market rate, then the bond will sell at a premium. So in other words, if say the coupon rate was 8% and my market rate was 6.7, then the bond would sell at more at a premium to the 100,000. So it'll sell at 100,000, plus something. And then number 6, if the coupon rate equals the market rate, then the bond will sell at face value. And number 7, bond prices primarily function of the difference between the coupon rate and the market rate, which I mentioned before. So this concludes the first section on valuation of value in a term bond.